Chemical compounds can be classified into two main types, based on how the atoms in these compounds are bound together. Compounds where atoms of metals are bound to atoms of nonmetals or halogens are ionic. In such compounds, the atoms of metals give up, in chemistry we say donate, one or more of their electrons and become cations. The atoms of nonmetals or halogens take, in chemistry we say accept, the electrons given up by metals and become anions. The positively charged cations and negatively charged anions attract each other and are held together by this attraction. In a solid, they arrange in a regular pattern on a lattice, forming what we call an ionic crystal. Unlike in metallic crystals, where the valence electrons released by metal atoms can travel throughout the entire volume of the crystal, and unlike covalent crystals, where valence electrons are shared between neighboring atoms, in ionic crystals, the valence electrons that are donated by the metal atoms are accepted by the non-metal atoms, or halogen atoms, and reside on the resulting anion. Because the total number of electrons in the ionic crystal is the same as the total number of protons, electrons are simply transferred from metal atoms to non-metal or halogen atoms. Ionic crystals are overall electrically neutral. A typical ionic crystal is sodium chloride, table salt. Table salt consists of sodium cations and chlorine anions at a 1:1 ratio. Sodium is an alkali metal, and its atoms have one valence electron, the electron in the 3s subshell. Chlorine is a halogen, and its atoms have 7 valence electrons, 2 in the 3s subshell and 5 in the 3p subshell. In table salt, each sodium atom donates its only electron to a chlorine atom. The resulting sodium cation, sodium plus, has the electron configuration 1s2, 2s2, 2p6 plus, or in shorthand notation, neon plus. The distribution of electrons among orbitals is the same as for a neutral neon atom, but the sodium cation has a positive charge that is equal in magnitude to the charge of one electron. The chlorine atom that accepts the extra electron becomes a chlorine anion, chlorine minus, and has the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6 minus, or in shorthand notation, argon minus. The distribution of electrons among orbitals is the same as for a neutral argon atom, but the chlorine anion has a negative charge that is equal to the charge of one electron. Another example of an ionic crystal is magnesium oxide that consists of magnesium cations and oxygen anions at a 1:1 ratio. Magnesium is an alkaline earth metal, and its atoms have 2 valence electrons, the electrons in the 3s subshell. Oxygen is a nonmetal in group 16 of the periodic table, and its atoms have 6 valence electrons, 2 in the 2s subshell and 4 in the 2p subshell. In magnesium oxide, each magnesium atom donates both of its valence electrons to the oxygen atoms. The resulting magnesium cation, magnesium 2+, has the electron configuration 1s2, 2s2, 2p6, 2+, or in shorthand notation, neon 2+. The distribution of electrons among orbitals is the same as for a neon atom, but the magnesium cation has a positive charge that is equal in magnitude to twice the charge of an electron. The oxygen atom that accepts the extra electrons becomes an oxygen anion, O2-, and has the electron configuration 1s2, 2s2, 2p6, 2-, or in shorthand notation, neon 2-. The distribution of electrons among orbitals is the same as for a neutral neon atom, but the oxygen anion has a negative charge that is equal to twice the charge of an electron. In both of these examples, we looked at compounds formed by a metal that donates the same number of electrons that the nonmetal or halogen accepts. Remember, alkali metals form cations with charge plus, alkaline earth metals form cations with charge 2+, halogens form anions with charge minus, and group 16 nonmetals form anions with charge 2-. Now consider the case of aluminum oxide, a compound that consists of aluminum cations and oxygen anions. Aluminum always donates 3 electrons and forms cations with charge 3+, aluminum 3+, and oxygen always accepts 2 electrons and forms anions with charge 2-. Therefore, an aluminum atom donates 1.5 times as many electrons as an oxygen atom can accept. In order to distribute all electrons that are donated by aluminum atoms among oxygen atoms, we need 1.5 times as many oxygen atoms as we have aluminum atoms. That is why in aluminum oxide, the ratio of the number of oxygen atoms to the number of aluminum atoms is 3:2. A basic unit of aluminum oxide consists of 2 aluminum atoms that donate 3 electrons each for a total of 6 electrons donated, and 3 oxygen atoms that accept 2 electrons each for a total of 6 electrons accepted. This composition of the basic unit of aluminum oxide ensures that it is overall electrically neutral, and therefore the aluminum oxide solid as a whole is electrically neutral. As we said earlier, ionic compounds form when a metal atom bonds with a nonmetal or halogen atom. When 2 nonmetal or halogen atoms bond with each other, they share electrons with each other and form a covalent bond. Chemical compounds that consist of only nonmetal and or halogen atoms are called molecular compounds. An example of a molecular compound is water. A water molecule consists of 1 oxygen atom and 2 hydrogen atoms. The oxygen atom has a total of 6 valence electrons. In a water molecule, it shares one of its valence electrons with one of the hydrogen atoms and another of its valence electrons with the second hydrogen atom. In turn, each hydrogen atom shares its only electron with the oxygen atom. These electrons are not completely transferred from the hydrogen to the oxygen, or from the oxygen to the hydrogen, but are rather found in the space between the hydrogen and the oxygen. The covalent bonds in molecular compounds are similar to the covalent bonds in homoatomic molecules of elemental substances that consist of 2 or more atoms of the same element, as we discussed in an earlier video. However, unlike the molecules of elemental substances, the molecules of molecular compounds are heteroatomic, meaning that they consist of atoms of 2 or more different elements. In terms of the number of atoms in the molecule, molecular compounds, just like homoatomic molecules, can be either diatomic or polyatomic. For instance, a water molecule is polyatomic, meaning that it consists of more than 2 atoms, 3, 1 oxygen and 2 hydrogens. A carbon monoxide molecule is diatomic. meaning that it consists of only two atoms, one carbon and one oxygen. There's a great variety of molecular compounds. Some are relatively small and simple, like water or methane, the natural gas that is used in gas stoves. Its molecules consist of one carbon atom and 4 hydrogen atoms that are bound to it. Others are more complex, like sucrose that consists of 12 carbon atoms, 22 hydrogen atoms, and 11 oxygen atoms. The bodies of humans and animals are mostly built from molecular compounds, including some very complex ones. We will talk more about molecular compounds and how exactly they form or covalent bonds are formed in them in a later lecture.